Alright, hello everybody. Welcome back to Calc 3. Plan for today is to do our quiz over Standard 1 and give you your first attempt at earning a mastery. And then we will jump into Standard 2, start talking about dot products. So just so you know, the current plan is to try and work our way through Standard 2 today and Friday, which means we'll be ready for Standard 2 quiz on Monday, if things go well. As far as office hours go, I've got my usual office hour this afternoon at 2 o'clock, and I have our office hours tomorrow morning at 10, and tomorrow afternoon at 1. As always, if you'd like to meet with me, there is a link you can sign up for on Blackboard. That'll let you reserve a time, and then link to my Zoom channel as well on office hours tab on Blackboard. No homework for today. Sometime today or tomorrow, I'm going to try and I'll post some practice problems for Standard 2 from the book, and but I have not gotten those yet. So, anybody have any questions or comments before I pass out the quiz? Why is it always a bad idea to try and teach horses analytic geometry? Because you should never put Descartes before the horse. So the way I usually do quizzes is I'll pass it out, and I'll usually let you know about how much time you have. This quiz, it's going to be about a 10-minute quiz. When you have about 45 seconds left on the quiz, I will I'll make an announcement. I'll say something along the lines of go ahead and start finishing up your thoughts. That means you have a little under a minute to go. And next question. All right, so go ahead and pass this out. When you're finished with the quiz, just turn it over. On your desk. If you want, you can draw a picture on the back. I always like seeing pictures of random things. And quiz is out now, so let's have quiet in the room, please. Go ahead and take a few seconds to finish your thoughts. And pass your quizzes towards the front of the room, please. Pass your quizzes forward. Okay, so since now we're moving on to standard 2. Hopefully, I have these quizzes back for you on Friday. But once I get these back, you will then be able to start requesting your first retest, which I will describe how to do on Friday. So new standard means a new packet. We're going to have a new one of these for every standard we go through. And this standard is going to be about a new algebraic operation that we can do involving vectors, namely taking dot products. And since it's a little more involved than the ones we've talked about so far, it gets its own standard. So we've talked about 2 algebraic operations that we can do with vectors so far. Anybody remind me what the two were from the last packet?
Addition and scalar multiplication.
Yeah, exactly. We talked about how to add vectors of the same dimension to produce a new vector. We've talked about how to take a vector and multiply it by a scalar to produce a new vector. And now, we're going to be, in the next 2 standards, we're going to be talking about 2 more operations that we can do involving vector algebra. Ways to kind of combine old vectors into new ones, into new information. And the one from standard 2 is going to be a dot product. So to start off, we're going to say, we're going to let V be the vector v1, v2, up to vn, and w be the vector w1, w2, up to wn, the vectors in Rn, and then the dot product of v and w is going to be this expression. We're going to denote it by having v, little dot, hence the name dot product, and w. And we're going to define that to be v1 times w1 plus v2 times w2 all the way up to vn times wn. So in other words, we're just going to peel off the first coordinates from these 2 vectors and multiply them together. Second coordinates from each of the 2 vectors and multiply those together. Keep going through this process until we get to the last 2 coordinates, which when we peel off and multiply together, we'll then get a bunch of expressions, v1, w1, v2, w2, etc., that we'll just add together at the end. And if you're a fan of sigma notation from Calc 2, you could also write it out like this if you prefer. the sum from I equals 1 to n of v sub I times w sub I. If you don't really remember sigma notation or you're not a fan, don't worry. You don't have to be able to do too much with that in this course. We'll talk about it kind of when we need it. So right off the bat, when we're looking at taking a dot product of two vectors in Rn, what sort of output are we going to get from the dot product? Meaning, when we take a dot product, are we going to get more vectors in Rn? Are we going to be getting scalar values? Are we going to be getting emojis? What sorts of things is the dot product going to produce when we apply it to two n-dimensional vectors?
Scalar.
Yeah. The dot product is not going to give us another vector. Whenever you take the dot product, it's going to produce a scalar value. Because v1, w1, etc. are all scalar values, which when you multiply scalars and add them together, you're still going to get a scalar. Meaning whenever you take the dot product of two vectors, you're always just going to get a number, a single number, no matter how big your original vectors were, as your answer. And so dot product's a little bit different in that, unlike with vector addition, which produces vectors, we're only going to get numerical values as outputs. And those numerical values, though, can still tell us a lot of interesting geometric information, though, about the relationship between the individual vectors, such as how long were the original vectors? What is the angle between those two vectors? Are those vectors perpendicular to each other or not? And those are going to be the sorts of topics that we're going to be looking at in this standard, is what does this scalar value tell you about the original v and w? So let's start off with a couple examples. Let's say I wanted to compute the dot product of 1, 2, 3, and the vector -4, 5, -6. There are two vectors in R3, so if we should be able to take their dot product and somehow end up with a scalar value. So if we multiply this out, we're going to get the sum of three different terms according to our dot product formula. What is the first term in this sum going to end up being?
-4.
It's going to be 1 times -4, which is going to come out to -4. How about the second term in our sum? It's going to be 2 times 5, which will come out to 10. And finally, how about the last term? We're going to get 3 times a -6, which will give us -18 v. Which, when we add these up now, we'll get -4 plus 10 is +6 minus 18 is going to come out to -12 as our solution. So we started with two vectors in R3. Answer is just a single number, -12. Let's take a look at another one. Let's look at what happens when we take the dot product of the vector 1, 2 and the vector 3, -11, 2. What happens when we try and take the dot product of these two vectors, do you think?
No, it's not possible.
It's not possible. Why not?
Because the vectors are in two different RNs.
Yeah, our first vector is in R2. Our second vector is in R3. And so if we were to try and take the dot product, we could try something like 1 times 3 plus 2 times -11 plus times +2. There's not enough terms in our first vector to be able to make this operation possible. And so just like with vector addition, if your two vectors aren't the same dimension, meaning they don't have the same number of coordinates, then the dot product is undefined. This is undefined since 1, 2, and 3, negative 11, 2 aren't in the same Rn. And so, in order to be able to take your dot product, you have to have two vectors in R2, two vectors in R3, two vectors in R5 trillion. They have to be the same dimension. So, does anybody have any questions or comments so far? I think it's a pretty straightforward definition. Computation is fairly simple, I would say. You're just peeling off all your coordinates. You're multiplying. You're adding. You're doing basic real number arithmetic in the end. The reason why, by the way, we call this the dot product of two vectors and not just the product is because we're going to have another way in the next standard of actually multiplying two vectors together that'll produce a new vector, and that'll be called the cross product. So we're calling this one specifically the dot product to disambiguate it from another term, which we'll see later on. So first thing I want to talk about that we can actually do with these dot products, first thing that would tell us why do we care about them, is going to be because the dot product is going to allow us to quickly find how long a vector in Rn is. In other words, it's going to tell us the length / magnitude of a vector. So this one is sort of like a hybrid definition / theorem, in that we're sort of defining what does it mean to take the length of a vector, and we're also saying here is what your intuitive idea of what length of an arrow, say, should be, and how you can relate that back to this definition here. So, given a vector of V in Rn, the length, or if you prefer, the magnitude of V is going to be given by this expression. Whenever we want to talk about the length of a vector, typically we'll just have V for the vector and then these double bars around it. And then the expression you can do to calculate the length of your vector is going to be square root of V1 squared plus V2 squared, etc., all the way up to V sub n squared, where V1, V2, etc. are the coordinates of V. And if we wanted to write that in a little bit of a simpler form, we could just write that as the dot product, or the square root of the dot product of the vector V with itself. So if you take V dot V and then the square root of that number, that is always going to give you the length of your vector V. And the cool thing is, this will tell you the length of a vector, say the length of your arrow in 2 or 3 dimensions. It'll also work to tell you the length of your vector in 4 or 5 or however many dimensions you want. It's not just restricted to the idea of length that you can necessarily visualize. So let's take a quick look at why this formula actually works the way it does. And we'll do that by looking at an example in R2. So it's kind of an example of where does this formula come from. Do the following. Let's say I have some arrow drawn out. Let's say we have this vector here, which I'll call V. And V is going to have coordinates V1, V2. So V1 will be the x coordinate of this point. V2 will be the y coordinate. and I'm interested in finding out the length of this vector v. So in other words, I'd like to know the length of the line segment that starts at the origin at 0, 0 and ends at v1, v2. If I were to give you this question, and say, if you're given this question in, say, I don't know, a Calc 1 class or something, how would you find the length of this line segment from 0, 0 to v1, v2? Ooh, the Pythagorean Theorem. How would we use the Pythagorean Theorem? Doesn't that involve having a triangle to look at?
So we could consider the vector to be the hypotenuse of triangle with the sides up to the v1 value, v2 value.
Okay, so maybe like a triangle like this, so to speak?
Yeah. And take the square root of these squares of both the legs.
Yeah, the Pythagorean Theorem tells us that if this is side A, this is side B, and if the hypotenuse is side C, that's going to tell us that a squared plus b squared equals c squared in a right triangle. That if you take the two shorter sides of your right triangle, a and b, the length of a plus length of b, or a squared plus b squared, has to give you the hypotenuse squared. And so now it would be nice if we could have like values in this specific picture that we could plug in for a, b, and c, perhaps involving v1, v2, and v somehow. So what's going to be the length of a here? In other words, what's the length of the bottom of this triangle going to be? I think it's going to be v1, because this point, the origin, is at 0, 0. This point right here is going to be at v1, 0. And so if you want to ask the question of how far apart are these 2 points, well, they're distance v1 apart. Just measure the change in the x-coordinate. So here our a is going to be v1. How about our b? What's going to be the length of the right-hand side of this right triangle? Yeah, v2. The distance from v1, 0 to v1, v2, well, just the change in height, which is v2. So our b here is going to turn out to be v2 squared. And finally, what could we plug in for c here? Here we don't necessarily have a nice scalar value we can plug in, but maybe something involving the vector v. What would the length of the hypotenuse represent in terms of v? Oh, sorry, did you ever read that? Never mind. Just the vector v? Careful. I'm not sure what we would mean when we say take a whole vector and square it, so to speak, or to set it equal to the scalar. I think you're close. It's good. It's definitely going to involve v somehow, but it needs to be just a scalar value here.
The magnitude of the vector.
I think we need the magnitude. If c here is just going to be a number corresponding to the length of this line segment, that's going to correspond to the magnitude of v. So this will give us the magnitude of v quantity squared. So that according to the Pythagorean Theorem, the magnitude of v quantity squared should be equal to v1 squared plus v2 squared. And then, if we take the square root of both sides, since both sides are going to be positive numbers, v1 squared plus v2 squared is never going to be negative. The magnitude of a vector is never going to be negative. We could just take the square root of both sides, and that'll tell us the magnitude of v by itself is going to be the square root of v1 squared plus v2 squared. which in R2 is the same as just being the square root of the dot product of v with itself. And so really, this formula for how to find the length or magnitude of a vector is really just boils down in the end to using the Pythagorean theorem. The cool thing though is that this not only works in just 2 dimensions, it works in 3 dimensions, 4 dimensions, 5,000 dimensions. You can talk about how to find, it's really telling you, here's how you find the length of a 15,000 dimensional arrow. Not something intuitively maybe that makes much sense, but algebraically you can encapsulate with this formula here. So what questions do you have before we move on to looking at a couple of specific examples? Okay. So let's try plugging this in a couple of vectors. So let's say we have the vector w is equal to 3, negative 4. We want to find the magnitude of w. Well, according to this formula, we're going to need to take the square root of something. What's going to be the first term that we have inside of our square root? It's going to be 3 squared, which when we evaluate that out, is going to come out to 9. Yep, I like that. How about the second term?
16.
Say that again?
16.
16. We're going to get negative 4 quantity squared, which negative 4 times negative 4 will indeed come out to a positive 16. And so then we simplify, we'll get the square root of 25. We take 9 plus 16, and square root of 25 is 5. Mosquito. This vector has length 5, which really is just going to correspond to the fact that 3, 4, 5 is a Pythagorean triple. That x-coordinate here, 3 squared, plus y-coordinate, negative 4 squared, is going to be the same as 5 squared. So if we graph this out, 1, 2, 3, 1, 2, 3, 4. Pretend that that's a straight line arrow. This vector right here is going to be length 5. Let's look at a little bit more challenging one. Let's say we want to find the length of the vector v, and this time it's not going to be given in standard form. I'm going to write it as 5i minus 2j minus 3k. What would we have to do if we wanted to find the magnitude of that vector? Enter.
Plug in the standard basis vectors and
Okay, so
multiply the scalars out.
So if we have our standard basis vectors, I is 1, 0, 0, our j is 0, 1, 0, and our k is 0, 0, 1. What would we get if we evaluated this out and actually tried to simplify 5i minus 2j minus 3k? Coming in.
5, negative 2, negative 3.
Yeah, we're just going to get 5, negative 2, negative 3. The same as the coordinates on I, j, and k. And so now, we can find the length of this vector in the same way. take the square root of x coordinate squared, y coordinate -2 squared, and z coordinate -3 quantity squared, which will give us square root of 25 plus 4 plus 9, which is 29 plus 9 is square root of 38. And can anybody tell me what square root of 38 simplifies to?
6 root 2.
6 root 2. Not quite, because that would be square root of 36 times square root of 2. That would be square root of 72. Okay. It doesn't. That's as simple as you can really get it, I think. You could write it as like square root of 19 times square root of 2, but neither of those are nice numbers, so square root of 38 is. And before you ask, Dr. Gerstel, how much would we need to simplify this on a quiz or something? I'm okay with leaving it in that. If you tried to leave your answer to the last question as square root of 25, you'll probably, which is technically correct, I'll probably draw a little frowny face on your quiz or something, but count it as correct. And say something like, learn how to take square root of 25. It's good to be able to simplify whenever you can, but something like this, square root of 38, you can't really do anything with. If you're curious, I think it's probably about 6.2 or 6.1-ish as the length of this three-dimensional vector. So that's kind of the first application of why do we care about dot products, because this dot product formula kind of gives us a nice way to measure magnitude. And in a couple standards from now, we're going to see some applications of why would you actually care about finding magnitude of vectors like this. Any questions before I start erasing stuff and move on to the next application? Yes, thanks. Well, do you want the magnitude of your vector to be, do you want the length of this this vector to be 5, or do you want it to also potentially be -5? I was going to say, I think we just want to include the positive number here, because we want all of our length / magnitudes to always come out to, we never want to get a negative number for our magnitude. That would be like saying, aha, I have this three-dimensional ruler, and my ruler is -3 feet long, not the sort of, I guess, negative yardstick. It wouldn't make physical really sense, so we're only going to include the positive square root. But otherwise you're right. If we had something like magnitude of v squared equals 4, technically, as a number, if we solve this, we could get the magnitude of v is plus or minus 2. But we typically only want to ever consider positive numbers or 0 as numbers that are okay to be magnitudes.
So the result of multiplying two vectors, like in the case of our first question,
What does -12 tell us? Well, I think we're going to see in our next application what's the significance of getting a positive versus a negative dot product. That is actually going to tell us some important relationship information about the two vectors. It doesn't necessarily tell us too much about their magnitudes, though, individually. Magnitude is really only helpful. You really only learn about magnitude when you take the dot product of a vector with itself. So let's look at the next page, and we'll start to maybe see how we can, what that -12 value might tell us about the relationship. How do these two vectors interact with each other? And specifically, it's going to tell us about how we can find the angle in between our two vectors. In other words, if, for instance, we have a vector here, A, and a vector here, B, we can actually use the dot product to tell us how big is this angle theta going to be between the two vectors. And spoiler alert, answer to your question, getting a negative value basically means that that angle is going to be an obtuse angle. So let's write this out. And this I'll write out as a theorem. If we let A and B be any two vectors in R2 or R3, so any two or three-dimensional vectors, then the angle theta between A and B is going to satisfy that cosine of theta is going to be equal to the dot product of A and B divided by magnitude of A times the magnitude of B. And so by combining information about the dot product of two vectors along with their magnitudes, you could find use this formula to help you find the angle between them. Dr. Gerstle, I see cosine. Are we going to have to do trig in this class? You're going to have to do a small amount of trig in this class. But I got you something to help you out. If you flip for just a second to the back page of your packet, you can, anytime that we're going to be doing some trig in a packet, I'll include this page at the back, and I'll also include this page on a quiz or an exam. If you want, you could rip that page off from the back, and this is just kind of something I'll always give you whenever we need to do some trigonometry. And so this front page here is a unit circle, and anytime you need to know something like, here's the thing, this is Calc 3 class, this isn't a trig class. I don't really care that much if you memorize what's cosine of pi over 3, or what's tangent of 7 pi over 4. I mean, you can memorize that, but I don't know, I don't like memorizing things if I can avoid it. So I'm going to give you this sheet, and then it'll be up to you to understand, like, how would you find, say, cosine of 7 pi over 4 from looking at this sheet? You'd be going to 7 pi over 4, look at the corresponding point, take its x coordinate for cosine, and that would give you, say, square root of 2 over 2. So let's see what happens. I'm going to try, oh, by the way, I don't want to prove this formula, because proving this formula just involves a bunch of trig identities, law of cosines. No thanks. It's not a particularly nice proof, so we're going to skip this one. Yes?
Well, curiosity then, is it applicable in dimensions higher than the third, or?
It is.
Okay.
If you have an idea of what do you mean by the angle between two 5-dimensional vectors, or 6-dimensional vectors, etc. If you have a definition for what the angle is, and what that definition is probably depends on whatever physical application you're looking at, you could totally apply this formula to vectors A and B in any number of dimensions, as long as they're the same. Because no matter what dimensions A and B are, you can always take their dot product, take their magnitudes, divide, multiply. That'll get you a scalar you can take inverse cosine of. Yeah, there's nothing specific to 2 or 3 dimensions. I only mentioned R2 and R3 here, because those are kind of the ones that we could sort of visualize angle between two vectors. Yes?
What's the B over N?
The B, oh, this?
Yes.
B/W, that's my shorthand for between. So the angle theta between A and B will satisfy this question. So, yeah, if I ever write something on the board and using some of my shorthand, because I have lots of shorthand I like to use because writing at the board takes up time, just let me know. But yeah, B/W, if you ever see me write that's going to be between. By the way, this is a calculus class, So all of our angle measurements are going to be in what units? Degrees or radians? It's going to be radians. And in particular, we're always going to choose theta. We want to find theta such that theta is between 0 and pi radians. Or if you prefer, 0 and 180 degrees. But since we're working in a calc setting, it's going to be radians, is going to be the answer that we care about. So let's do an example. Let's say we have two vectors. Our vector v is going to be I plus j, and our vector w is going to be j plus k, and our goal is going to be to use this formula to find what exactly is the angle between these two vectors. So I plus j, j plus k, we need to find the angle between the two vectors. So first of all, can anybody tell me how we can write the vector w in standard form? Just j plus k? Yeah?
0, 1, 1.
0, 1, 1. We have 0i, so the first coordinate is 0, with a 1j, so 1 for second, and a 1 for k, our third coordinate. How about our first vector, I plus j? Yes.
1,
1,
1.
1? Like that? I have a bit of an issue here. And I'm trying to, and it looks like we're asking, what is the angle between this two-dimensional vector and this three-dimensional vector? Which I think we might run into trouble because right off the bat, we won't be able to take the dot product of those two vectors because they're not the same dimension.
Can we assume that the standard basis vectors I and j are in R3 if the ones for w are in R3?
I think we have to assume, yeah, that this first vector v is something in R3 rather than in R2, because otherwise we're going to get stuck very quickly. So how could we write this? So how could we rewrite vector v in as I plus j to be a vector in R3 instead of R2?
1, 0.
I think we could put a 0 at the end. Yeah, good observation. So here, I purposely wrote it this way to be a little bit ambiguous. Does I plus j mean the two-dimensional vector 1, 1, or does it mean the three-dimensional vector 1, 1, 0? You kind of have to know that just from looking at the context. Since our other vector w is a vector in R3, we have to assume that v is going to be a vector in R3 as well, and go with this one rather than that. If w had been a vector in R2, then we probably would have just chosen 1, 1 to be our choice of v. So what we're really doing is we're trying to find the angle between these two vectors.
So what's to say they're not in the fourth dimension?
They could be. Well, they could be in R4, in which case we'd be looking at 1, 1, 0, 0, 0, 1, 1, 0.
So would that change the angle line?
Don't think so. I think if we use these two vectors in R4, it would come out to the exact same answer. And the reason why involves the fact that these two vectors are the same as these two vectors projected downwards into R3. Messy topological math terms. These two vectors in R4 basically correspond to these two vectors in R3. In a nice way that makes it so dot products will be the same, the magnitudes will be the same. Just tacking 0 at the end of a vector algebraically will make things change, but geometrically doesn't really change much. If that makes sense. That's a good question. How do we know we're not, Dr. Gerstle isn't pulling our leg and we're working in R27 with like 24 zeros at the end of each vector? Answer is, even if I was, it doesn't really matter. So before we actually go through and do the algebraic calculation, I thought we could instead take a quick break and look at a graph of these two vectors. And I want to get your all's opinion on what you might guess the angle comes out to about. Oh, why'd you turn off? Dang it. Vector's supposed to be on, and I just click a button and boom, it appears, but it turned itself off because it's trying to save energy settings or something. So we're looking for the angle between 1, 1, 0 and 0, 1, 1. Okay, here it is. I've already sort of graphed it out here. So here's our two vectors. It's based on what these two vectors look like. Would anybody like to make a guess as to what the angle is going to approximately be? Just from trying to eyeball the picture. Pi over 3? Think it looks like about 60-degree angle? Well, let's see. I think that looks reasonable. It looks less than 90 degrees, but not by that much. So pi over 3 or 60 degrees. It's maybe reasonable. Any other guesses? So it looks like this is about a 60-degree angle. Pi over 3. I don't know why I keep saying degrees. I'm a calculus professor. Say everything in radians. Turn that off for a second, do the calculation, and see if that's what we get. So theta is going to have its cosine. Cosine theta is going to be v dot w divided by magnitude of v times magnitude of w. If we take the dot product of v and w, we're going to get 1 times 0 plus 1 times 1 plus 0 times 1. See, magnitude of v is going to be square root of 1 squared plus 1 squared plus 0 squared. Magnitude of w is going to be 0 squared plus 1 squared plus 1 squared. The numerator, we're going to get 0 plus 1 plus 0 is just going to come out to 1. In the denominator, 1 squared plus 1 squared plus 0 squared is 2, so we'll get a square root of 2. 0 squared plus 1 squared plus 1 squared is also, square root of that is also square root of 2. What is this expression? 1 over square root of 2 times square root of 2 going to simplify to? Yeah, square root of 2 times square root of 2 is just going to be 2. So this comes out to a half. And now we have to ask the question, what angle between 0 and pi is going to have cosine of a half? So if you go to the top half of the unit circle, which angle is going to have a point whose x-coordinate is positive 1/2? Pi over 3. Turns out our estimate was correct. Theta is going to be pi over 3 radians, or if you prefer, 60 degrees. So, I forget who guessed pi over 3, but good guess. So take your dot product, divide by your magnitudes, and then to see cosine of what angle is going to give you this. Let's look at one more example really quick. Let's change our two vectors being two-dimensional vectors, 2, 5, and negative 10, 4. Yeah. I'm used to having one of these, just I push a button and it goes down. There. So now, let's erase these two vectors. We're going to put in a new vector. It has to be three-dimensional, so I'm going to put it in as 2, 5, 0. Which will make it blue, and we'll make it extra wide. There's our first vector. Second vector. It's going to be -10, 4, 0. 4, color blue, and we'll change our axes, go from -10 to 10, -10 to 10. So if we try to look at it in the XY plane, it would look something like this. Any guesses as to what this angle is going to come out to be?
Pi over 2.
Think it looks like a right angle? Looks that way. I can see this being about a 90-degree or a pi over 2 radian angle. So let's see if that's right. So, so if we take a look at 2, 5 and -10, 4, we'll get packing up. There's still a good 2 minutes left in class. We'll get that cosine of theta is the dot product, 2 times -10 plus 5 times 4 over square root of 2 squared plus 5 squared, and square root of -10 squared plus 4 squared. 2 times -10 is -20, plus a positive 20 is going to be 0 divided by, oh wait, it's 0. Who cares what the denominator is? As long as the denominator is not 0, which I can tell it's not going to be, it's going to come out to 0. So that cosine of theta is 0, which means theta, look at the graph, is in fact going to be pi over 2 radians. I'm absolutely correct. And so, what's going to turn out to be the case, if you were to take the dot product of two vectors and get 0, we're going to see kind of, and more generally next class, that that's always going to correspond to having a right angle between the two. Right, when we come back on Friday, we're going to try and finish Standard 2, where we'll talk about what it means for two vectors to be perpendicular and higher dimensions, as well as kind of look at some more algebraic properties of the dot product. Kind of we'll prove another theorem about how it works. Hope you all have a good rest of your day. I will see you all on Friday. Feel free to send me an email or sign up for an office hour appointment if you have anything you'd like to talk about.
I mean, I don't, they're not kidding. Yes. Yes.
I just wanted to interpret this because I'm pretty familiar with vectors,
So you just took this quiz, okay?
Yeah.
Okay. Yeah. In the future, though, how about this? How about you let me know before a quiz if you'd like to just take it outside of class, and we'll try and make it sounded like from the email 2 o'clock might be a good time for like a. So, and I'll give you time and a half from based on whatever class is. So for 10 minutes, that'd be 15.
That sounds good.
And you said you had swim practice at 3:30?
3:15.
3:15. Okay, so we'll need to do something different when it comes time for exams, but we can
The other thing,
figure that out closer.
for Western Heritage, test last year, I would test with the deans. So if like we have a class at 1 or something, I could go up to the deans at 1 and take it there.
Oh, they do that.
Yeah.
Didn't know that. That opens up new possibilities for me. Okay, we'll talk about that in like a couple days before, a few days before the exam, and figure something out.
All right, thank you.
It'll either be that, or just you find another time for you to just come in and sit in a Mac party. Appreciate the heads up. Let me know if there's anything else I can do to help. Oh, forgot to turn this off.